Hello everyone. Let us continue the fourth part of today's class. Okay. In the third part, we have taught to page 110. Okay, we are talking about section 1.3.5.1. Architecture of the DQN used in the DQSA algorithm. We illustrate the architecture of the multi-user DQN used in the DQSA algorithm in figure 1.4. Okay, figure 1.4 is an illustration of the architecture of the multi-user DQN used in DQSA algorithm. So first there is an input layer, and there is a LSTM layer, 100 units, and this block will output two block, advantage layer 10 units and the value layer 10 units. And here is the A of SA, here is the V of S. Okay, where A denotes the advantage and S is the state, A is the action, and V is value, S is state. And these two blocks both input to this the final block, which is the Q of SA. Q is the Q value. Okay. We next explain each block in the DQN. Okay, first input layer. Okay, this one, input layer. The input xn of t to the DQN is a vector of size 2k plus 2. Okay. The first k plus 1 input entries indicate the action, that is, selected channel taken at time t minus 1. Specifically, if the user has not transmitted at time slot t minus 1, the first entry is set to 1, and the next capital K entries are set to 0. If the user has transmitted its data on channel small k at time t minus 1, where 1 is smaller than or equal to small k, and small k is smaller than or equal to capital K, then the small k plus 1th entry is set to 1, and the remaining capital K entries are set to 0. The following capital K input entries are the achievable data rate of each channel when the channel is free, which is proportional to the channel bandwidth. The last input is 1 if an X signal has been received. Otherwise, if the transmission has failed or no transmission has been executed, it is set to 0. 2 LSTM layer. Okay, we can see that this is the LSTM layer, okay, which has 100 units. The complex network model that we handle involves partially observed network states by the users and non-Markovian dynamics determined by the interactions between the multiple users. Therefore, classical DQNs do not perform well in these cases. To tackle this problem, we add an LSTM layer. Okay, please see Host Connect and Stone 2015. Okay, we can see this. Okay, Host Connect and Stone, and the paper title is Deep Recurrent Q-Learning for Partially Observed NDPs, which is an archive preprint in 2015. To the DQN that maintains an internal state and aggregates observations over time. The LSTM layer is responsible for learning how to aggregate experiences over time, which makes it possible to infer the true network state based on the history of the process. 3. Value and advantage layers. Okay, this is the value layer, okay, which has 10 units. And this is the advantage layer, which has 10 units. Another improvement that we incorporated is the use of dueling DQNs, as suggested in Wang et al. 2015. Okay. Oh, sorry, this is an invalid hyperlink again. So I need to go to Wang et al. Okay, Wang. Okay, Wang et al. 2015. Okay, I will fix this problem. To solve the observability problem in DQNs, the idea of using dueling DQNs is to estimate the average Q value of the state V of Sn of t. Okay, that is the value independently from the advantage of each action. This operation mitigates the effect of states that are good or bad, regardless of the taken action. Okay, specifically, when we input Xn of t to the dueling DQNs, we update the Q value for selecting action An of t at time t by. Okay, Q of An of t. Okay, this means the Q value of the selecting action An of t, and this is V plus A of An of t, where V is the value, okay, and A is the advantage, okay, of An of t, and An of t is the selecting action, and this left arrow means we assign this value to this variable. Okay, note that both V and capital A of small an of t depend on the hidden network state Sn of t. The term V is the value of the state, and it estimates the expected Q value of the state with respect to the chosen action. The term capital A of small an of t is the advantage of each action, and it estimates the Q value minus its expected value. Okay, for block output layer. Okay, let us return to block output layer. Okay, this Q of SA. Okay, the output of the DQN is a vector of size capital K plus 1. The first entry of the output vector is the estimated Q value if the user chooses not to transmit at time t. The small k plus 1's entry, where 1 is smaller than or equal to small k, and small k is smaller than or equal to capital K, is the estimated Q value if the user chooses to transmit on channel small k at time t. Okay, sorry, the block output layer should be these two blocks. Okay, and this is the final block. Okay, 5. Double Q learning. Okay, finally, standard Q learning and DQN that use a max operator. See equation 1.10. Okay, this is equation 1.10. Okay, we have seen this in today's class earlier. Okay, are based on the same values for both selecting and evaluating actions. This operation tends to select overestimated values and causes performance reductions. Hence, another component that we add when training the DQN is the use of double Q learning. Okay, see Van Hasselt et al. In 2016. Okay, Van Hasselt et al. Okay, this is the paper title is Deep Reinforcement Learning with Double Q Learning in AAAI in 2016. To decouple the selection of actions from the evaluation of the Q values. Specifically, we use two neural networks referred to as DQN1 and DQN2. The selection of actions is done by DQN1, and the estimation of the corresponding Q value is done by DQN2. Okay, next let us go to section 1.3.5.2. Training the DQN and online spectrum access. We start by describing the pseudocode for training the DQN. Okay, training the DQN is done for all users at a central unit in an offline manner. Note that the training phase is rarely required to be updated by the central unit. Only when the environment characteristics have been significantly changed and no longer reflect the training experiences. The users communicate with the central unit and update their DQN weights from time to time. In real time, each user, say small n, operates in a fully distributed manner by making autonomous decisions based on the trained DQN. This allows users to learn efficient spectrum access policies in a distributed manner from local ECK signals only. Specifically, in real time, each user, say small n, accesses the spectrum as follows. First, at time slot t, obtain observation On of t and feed input Xn of t to the trend dqn1. Generate output Q values Q of A for all actions. A is in the set 0, 1 to capital K. Second, play the following strategy sigma n of t. Draw action an of t according to the following distribution. Okay, the probability of an of t is equal to A is equal to 1 minus alpha times exponential beta times Q of A over summation A tilde is in the set 0, 1 to capital K and exponential beta times Q of A tilde plus alpha over capital K plus 1 for all small a is in the set 0, 1 to capital K. For small alpha which is greater than 0 and beta is the temperature as in simulated annealing techniques. In practice, we take alpha to 0 with time, so that DQSA algorithm tends to choose actions with higher estimated Q values as time increases. Okay, this is the DQSA algorithm training phase. Okay, the first line is a for loop for iteration. Small I is equal to 1 to capital I. Do the following instructions. And the second line is also a for loop for episode. Small m is equal to 1 to capital M. Do the following pseudocode. And the third line is also a for loop. Okay, time slot small t is equal to 1 to capital T. Do the following pseudocode. And the fourth line is also a for loop. For user small n is equal to 1 to capital N. Do the following pseudocode. So there are 4 nested loop here. Okay, 4 nested for loops here. Okay, for line 5, observe an input Xn of t and feed it into the neural network DQN1. The sixth line is to generate an estimation of the Q value Q of A for all available actions. Small a is in the set 0, 1 to capital K by the neural network. Okay, the seventh line, take action an of t which is in the set 0, 1 to capital K according to equation 1.13. Okay, this is equation 1.13. This equation. And obtain a reward Rn of t plus 1. The eighth line, observe an input Xn of t plus 1 and feed it into both neural networks DQN1 and DQN2. The ninth line, generate estimations of the Q value tilde Q1 of A and tilde Q2 of A respectively for all actions A is in the set 0, 1 to capital K by the neural networks. For the 10th line, form a target vector for the training by replacing the an of t entry by this. Okay, q of an of t, okay, is replaced by this equation. Okay, Rn of t plus 1, it is the reward at time slot t plus 1 of user small n, and plus q tilde 2. Okay, q tilde 2 of a is here. And find the argument maximum of q1 tilde of a, and for all action a. Okay, q1 tilde of a is obtained in the ninth line. Okay, and what is argmax? Okay, this is to find the maximum of q1 tilde of a and output the corresponding a. Okay, and in this input to the function q tilde 2. Okay, so line 11 is N4. Okay, line 12 N4, line 13 N4. Okay, so these three lines end the for loops in line 2 to 4. And for the line 14, train dqn1 with inputs x and outputs q's. Okay, 15. Every L iterations set q2 to q1. Okay, this means that we set the value of q2 to q1. Okay, that is assign the value q1 to the variable q2. And finally, line 16 and 4. Okay, it is to end the for loop in the first line. Okay, and all iterations. Okay, so next we are going to see the 1.3.5.3. Okay, simulation results. In this subsection, we provide numerical examples to demonstrate the effectiveness of the DQSA algorithm. We thank Dr. Oshiri Napastek for generating the figures used in this section. We refer the reader to Napastek and Cohen 2018. Okay, this one. Okay, Napastek and Cohen. The paper title is Deep Multi-User Reinforcement Learning for Distributed Dynamic Spectrum Access, which is published in IEEE Transactions on Wireless Communications in 2018. And this is the DOI. When you click on this hyperlink, okay, and your browser will open this web page, and you can download a PDF of this paper. Okay, like this. Okay, let us go back to the slides. Okay, we refer the reader to Napastek and Cohen 2018 for more details regarding the training mechanisms. We start by investigating the channel throughput of the DQSA algorithm and compare it to slotted Aloha with an optimal attempt probability. Note that both idle time slots in which no user accesses the channel, as well as collisions in which more than two users access the channel at the same time slot, decrease performance. The channel throughput in this simulation is the fraction of time that packets are successfully delivered, where no collisions or idle time slots occur. Note that the slotted aloha, okay, it is 25 minutes. See you next time. Goodbye.